Let's continue Chapter 6. We're on 6.3, Applications for Normal Distribution. So the main idea here is to extend our discussion on normal distribution beyond the standard normal distribution where the mean is not 0 or the standard deviation is not equal to 1. We've gotten used to that with the calculator commands already because we're using our normal CDF and our inverse norm where we insert our mean and standard deviation. So there's really not going to be that much more different in terms of our calculator commands. So let's see how that's going to work out for us. Just to show you what they do in the book and what they need in the book to always refer back to the table A2, refer back to the standard normal distribution. They need to convert all the x values into z-scores. And so if you recall the z-score formula, this is our z-score formula, they convert everything to a z-score so that they can use a normal distribution. They can change your regular normal distribution through the z-score into a standard normal distribution where the mean is 0 and the standard deviation is 1. So let's take a look at an example. This is an example that we have. I actually have, we're going to do our work on a separate application, so let's take a look at our application here. So there's a safe load for a water taxi, and they found that to be 3,500 pounds. We note that the mean of a passenger is assumed to be 140. Assume the worst case scenario that all passengers are men, and assume that the weights of men are normally distributed with 172 pounds and a standard deviation of 29. If one man is randomly selected, what's the probability that he weighs 174 pounds, or he weighs less than 174 pounds? So recall that the way I want you to do this is to always start off with a drawing. Our drawing will help us figure out our minimum and maximum values. Now we do have a non-standard normal distribution, so we should denote our mean, 172. Maybe we can write that off to the side somewhere that our mean is 172 pounds. And our standard deviation is 29. So if one man is randomly selected, what's the probability he weighs less than 174? So 174 would be somewhere over here, a little bit greater. And we want less than that. So by doing this graph, we're able to establish our minimum and our maximum values so that when we do the normal CDF, we get the low and the high. So our probability that a randomly selected person is less than 174 pounds would be equal to, our calculator command would be our normal CDF. Our low would be minus infinity. Our high would be 174. And this is where our mean and standard deviation come in. Mean is 172, and our standard deviation is 29. So let's take out our graphing calculator. Our graphing calculator coming up. And we want to just do a distribution, and our normal CDF is the second one. And then we got negative infinity, so that's minus 1. And then the e to the 99, so that's going to be a really large number to the negative direction. We have a comma, we got 174, and then our comma, our mean is 172, and our standard deviation is 29. Okay, so after all that, it looks like the probability is 52.75%. So this is our percentage. Let's just finish off by writing down our answer, 0.52749, or 5. So that is the probability that a randomly selected person is going to weigh less than 174 pounds. Okay. All right. So if we had done it differently, then if we had done it with the way the book does it, what they would do first is they would find the z-value using the z-value formula. So this is x minus the mean divided by the standard deviation. That's 0.07. And they would take the z-value of 0.07 and look at table A2 and come up with the same probability that we got, 0.5279. Actually, now that we look at it, our answer was 0.52749, or 75 if we were to round off. Our answer is actually more precise than the answer that they would have found in table A2. And so I would go with our answer, and I would say that's our answer is correct. Okay. A few things to keep in mind. We did two types of problems there. We did a problem where we found the probability, and then there's also problems where you need to find the z-score given the area. And so with the business about looking at the right side or left side of the graph, I don't think that would be a big deal if we were to do things consistently with our graphs and using the calculator commands. I think it would be more of a big deal if we were using the table. And then the z-score negative on the left on the standard normal distribution. And then remember that the areas have to be positive. Okay, let's try to see if we can find our z-values or our x-values if we're given a particular probability. So this is what they have for for the step-by-step process. Again, this is a step-by-step process if you're trying to find the x value or a particular value using the table. We're not going to use a table. Just to keep in mind though, they took their z-score formula, and instead of having z equals, they solve for x, and then they use some simple algebra there to solve for x. Okay, so that's where that comes from. Anyways, we're actually not going to do that, so let's take a look at this problem where if we use the same data, we want to know what separates what determines the weight that separates the lightest 99.5% from the heaviest 0.5%. So we're going to use, just like we did before, we're going to use the inverse norm, but instead of having a mean of 0 and standard deviation of 1, we're going to put in this mean of 0, or mean of 172 and standard deviation of 29. So let's take a look at that. So if, say we're given this particular problem here, what I would expect you to do is well, we saw the graph already, but let's say we didn't see the graph, then we would come up with our own graph. And we'll assume, it's not written here, but it was given in an earlier problem, that the mean is 172 and our standard deviation is 29. So in our x values, we got 172. The 29 comes into play somewhere else here that we don't need to worry about. What we do need to worry about is we need to figure out what number it is we're looking for. So this is the value that we're looking for that separates the heaviest 0.05%, or I'm sorry, that's 0.5%. And what we want to do is we want to transfer or translate this into an actual value. And then what that's going to leave us is area on this side being 1 minus this thing, or 100% minus this thing. Actually, let's write this as a decimal already. So that's 0.0 1, so that's 0.005. So this value here, or the area to the left, is 1 minus 0.005, which I think is 0.995. And that's what we need, is we need the area to the left. So to find out this value, we're going to use the inverse norm. And then the first argument in the inverse norm is the area to the left, and the area to the left is 0.995. And we have a mean of 172 and a standard deviation of 29. So let's punch that into our calculators. And we go second function, distributions. The inverse norm is the third one. Inverse norm 0.995, throw a comma, oops, there isn't a 0 that came there, so a comma, 172, and then a comma, and then a 29. Okay, so we got 246.69 or 0.7. So that is going to be the value that we'll put here. It's let's call it 247. Okay, so that should be the value that we're looking at, or the value that we're trying to find. So if you would have done it using their process, you would have had to figure out the z-score that's associated with that area, and then from the z-score convert that to an x, which gives us the same value, which is 247. That is the same value that we got, except we got it without having to do any of those strange conversions that they're asking for. Okay. All right, so that takes care of that this particular section. Again, it's just like the standard normal distribution, except our mean is in standard deviation, not 0 and 1. Okay, the next section is talking about sampling distributions, and this theoretically is kind of a deep topic. What we're going to do is we're going to cover it lightly, and so I'm just going to breeze through some of these slides and try to look ahead to inferential statistics, which is the main goal of this section. It prepares us to looking into the inferential statistics. So the idea here is to try to get a grasp of what it means to sample distributions, and in sampling the distributions we'll see that we're going to pick a particular sample size, and then we're going to assume that we're going to be able to take all the possible samples of that same size from a population. And so that's the idea of sampling. Well, more precisely, the definition of sampling distribution. The sampling distribution of a statistic is a distribution of all values of the statistics when all possible samples of the same sample size are taken from the same population. So that's the idea. Now, of a statistic, so let's figure out which statistics we can use to do sampling distribution. And so the first one is going to be a proportion. A sampling distribution of a proportion is a distribution of sample proportions with all the sample sizes having the same size n. Okay. So it says here that the properties or the proportions tend to target the value of the population proportion. So that's what we're going for, is that we're looking for statistics that kind of hone in when we take a bunch of samples with the same sample size over a period of time, over this infinite number of times that we're going to take the sample. Maybe it's not infinite, but over a tedious process of just even imagining taking the same sample size, all the possible sample size that we can take for a population, that certain statistics would tend towards the actual population proportion and our population parameter, and a proportion is one of them. So under certain conditions, a distribution of a sample proportion can be approximated by the normal distribution. So that's another important aspect. And again, these are all previews of what kind of inferential statistics we can take when we get there in Chapter 7. Another statistic that we can use for sampling distributions is the mean. Okay. So with all the same sample sizes taken from the same population, the sampling distribution in the mean is typically represented as a probability distribution in the format of a table or a histogram or a formula. So the mean is another one that we can take, we can extend our inferential statistics. The value of the statistics, such as a sample mean, x bar, depends on the particular values included in the sample, and generally varies from sample to sample. The variability is called the sampling variability. All right. We don't need to worry too much about that. Let's move on. Estimators. Some statistics work much better than others as estimators of the population. So let's take a look at which we can estimate. So this is a kind of a strange scenario, and this is an example that they have in the book. If you can follow this, and that's great. If not, I wouldn't worry too much about it. I think it's just a concept that's kind of important to bridge the ideas between descriptive statistics and inferential statistics. So population let's say, as an example, we have just a population of 3 numbers, 1, 2, and 5. And then our sample sizes would be a size 2. Now they use this particular example because we can actually picture this, and this is a small enough population with 3 things, and the small enough difference between the population and the sample size is 2, that we can actually make a list of things. So out of these sample sizes of 2, there are 9 possible samples, it turns out, and that's why we can list them all, because we have a small population. Now realistically, our population can be as huge as 6,000, or even having a population size of 20 or 30 would be really big, and then we get sample sizes of smaller samples, then there'll be a really a lot of possible samples. But in this case, just to keep it simple, a population of 3 things and sample sizes of 2. For each sample, find the mean, the median, the range, the variance, and standard deviations. And so we're just going to look at these things to find for each sample. And then we'll see that if we take the average or the mean of those things, we'll see which ones would be good things to estimate. So let's take a look at the table. So this is a table found in your book. So these are all the possible samples in our population of 3 things and sample sizes of 2. And we got the means, the medians, the range of these samples, the variances, standard deviation, the proportion of odd numbers, the probabilities, and things like that. So what they asked us to do was to find the mean statistic value, the median, the average, the mean of all these medians, the mean of all these ranges, the mean of all these variances, the mean of all these standard deviations, etc. Now, since we know the population is 1, 2, and 5, there's only 3 numbers in there, we can actually calculate the mean. So we can actually calculate the median, calculate the range, calculate the variances, etc. Now, if we do all these calculations, we'll notice what matches. Our mean matches. Our median, 8.3 versus 2, does not match. Our range doesn't match. Our variance matches. Standard deviations didn't match. And our proportion matches. So these 3 things, our mean, our variance, and our proportion, would be the 3 statistics that we're going to focus on and be able to use to make inferences about the population parameter, because it looks like it can match up for us. Okay? So that's the whole idea behind the sampling distributions, is to figure out which statistics would best match our parameters. Now there's a second part of that question that they were asking. For each statistic, find the mean from part A. So we figured that out already, and then we got the solutions. So when using the sample statistics to estimate the population parameter, some statistics are good and some are not so good. If you have good statistics, then those are called unbiased estimators. And the target population parameters for us will be the mean, the variance, and the proportions. Some statistics that are not good targets for the population parameters are the other ones that we found. So we'll be focusing, like I said, on the mean, the variance, and the population when we study inferential statistics in Chapter 7. Okay. One more section in this chapter will tie in our study with the normal distribution, and this is called the central limit theorem. So the idea here is that based on all that we've learned, it turns out that if we do all the sampling for estimating population parameters, one of the best distributions for us that we're going to be dealing with would be the normal distribution. There's some cases where the normal distribution might not be good enough, and we'll be introduced to some new distributions later on when we study inferential statistics. But for now, we're going to focus on the normal distribution. And the central limit theorem has given conditions and conclusions. So there are 2 conditions that we're looking for. So for a central limit theorem, we have to be given that the random variable has a distribution which may or may not be normal. and then you can find the specific mean and standard deviation. The second condition that has to be given is that the sample sizes, simple random samples of size n are selected from the population, and so it's going to be important for us to be able to identify the sample sizes that we're going to take. So this is like the sampling distributions that we were talking about. So now our conclusions are as follows. So the distribution for the sample x bar will be the same as the distribution for a sample x bar will, as the sample size increase, approach normal distribution. So remember that the original distribution may or may not be a normal distribution. That could be a uniform distribution, that could be a skewed distribution. But if we collect the sample sizes and find the mean of the sample sizes, then our distribution will start to become normal. The mean of the sample means is going to be the same as the population mean, and that's going to be mu. Now the standard deviation of the sample means is not going to be the same as the original standard deviation of the population, but instead it's going to be the standard deviation of the population divided by the square root of all the sample sizes. So as a theorem, this might be kind of difficult to grasp, but I'm more interested in the practical uses of these things. Well, we're going to take a look at some practical examples. But they want to include a couple of other conditions that would be useful here. So practical rules or guidelines is that for sample sizes larger than n, the distribution is the same. For the sample means can be approximated with a normal distribution. So usually we like to have large sample sizes. And then the approximation gets better to a normal distribution as n gets larger. And then the second rule that they have here is that if the original population is already normally distributed, then the sample means will be normally distributed for any sample size. Okay, so this just discusses the size of your sample that you're dealing with. We have the notation. The mean for the sample sizes that we're using is going to be mu sub x bar. Now, because that's just equal to mu, it's not going to be that big of a deal for us to use mu sub x bar, because we can just use the population mean. Not a big deal. However, the standard deviation for these sample means is not the standard deviation for the population, and so this is where our sigma sub x bar will be important to use as a notation. And this is sometimes called the standard error of the mean. Alright, let's take a look at an example. So this example used a computer to generate 500,000 random digits and group them into 5,000 samples, each of 100. So there's 100 samples, or our sample sizes are going to be 100 each, and then they looked at the 5,000 samples. And so if they take a look at that distribution, it looks pretty uniform. Now we start increasing the sample sizes, then that distribution is going to look more and more normal. Okay, let's get past the theory behind this thing and actually take a look at an example. This is an example that has two parts in it, and one part will not use a central limit theorem, the other part will. And so this is where we can really see the central limit theorem in action, if we can see it as compared to something that doesn't have that doesn't use a central limit theorem. So let me see if my my notes have this already. Okay, I don't have this, so let's take a copy of this. And let's put it somewhere that we can annotate. So this is the problem that we're going to be dealing with. Now, if we take a look at this, this looks very similar to problems that we've already done. So, for example, we're taking a look at given a population that has a normal distribution with a mean of 172 pounds and a standard deviation of 29 pounds. If one man is randomly selected, find the probability that his weight is greater than 175. So this looks very familiar. 172, 175 would be bigger than that, and it's greater. So we shade in that region. So we would be looking at this as what is the probability that the variable is going to be bigger than 175 pounds, and this will take in a normal CDF of so the low is 175, the high is infinity, the mean is 172, and the standard deviation is 29. So those are the four things that we would be looking for. Now let's see if we can pull out our calculator now. And just do this calculation. So second function vars, normal CDF, and we have 175, comma, and then we have infinity, which is 1 e to the 99, and then the mean is 172 and the standard deviation is 29. So this is 45.88%. 0.4588. So this is our probability. So if we select one person, the probability that one person his weight is bigger than 175 is about 46%. Now let's do this one. This is a little bit different. Now the first one, they ask if one man is randomly selected, so you're pulling this one guy from the whole population. Here they're asking you if 20 different men are randomly selected. So n is equal to 20. The problem begins with n is equal to 20, so that means we're looking at a sampling distribution here. Find the probability that their mean weight is greater than 175 pounds, so their mean weight here. So we can begin by doing the same business of graphing, just to give us a good idea of what our high and our low values are. And so far it's looking the same as the first problem, but now we're actually looking at the mean distribution, so the probability that our mean distribution is bigger than 175. So this is where it begins to be different. So our notation here is just for any x from the population. Here we're looking at groups of 20. Our x bar is bigger than 175. So we do the same thing. We got normal CDF and 175 infinity. The mean is So this is where it begins to change a little bit. Well, this one doesn't change because remember the mean for a sampling distribution is the same as the mean for the population. Now the difference is, I identified the mean here, mu is equal to mu sub x bar, which is equal to the same thing, 172. But it turns out that our sigma of x bar is equal to, well, it's not just equal to 29, but it's equal to 29 divided by the square root of whatever n is. In this case, it's 20. So it's 29 divided by the square root of 20. So we have a new standard deviation to put in. And you can do this calculation separately, or you can just have the calculator do everything for you. So let's punch this into our calculator. And we're essentially going to have the same setup that we had before. Normal CDF, 175, 1e to the 99. And then our mean is 72. Now our standard deviation is not just 29, but it's 29 divided by the square root of 20. So if we punch that in, and that becomes 32.18%, or 0.3218. So that's different from the 45%. It's a little less likely for this thing to happen, it turns out. So let's take a snapshot of this and put it in our notes. And this would be our values. So let's just take a look at how they did it. They did it using the table. I mean the PowerPoint presentation. So what they did was they convert everything back into a z-score. Now you don't have to worry about this. We're just going to take a look at the final answer, but this is a step-by-step that they take. So they take a look at the z-score and they figure out the probability that's bigger than that, and they got 0.4602. So that was, how did that compare to ours? Compared to ours, we got 4588. So again, ours is more precise, so don't worry about that. So that's part A. Part B is that they take the standard deviation, and instead of 29, they have 29 over root 40. And so when they do that calculation, the result is 0.3228. And how did we compare? Uh, 0.3218. So again, came close. And again, ours is more precise, more exact, so we can be happy with that. So let's see if we can put these two ideas together. So the result was about 46% and for one person, and about 32%. So it looks like it's much easier for an individual to deviate away from the mean, because the mean is 29, and when you take 29 divided by the square root of 20, it gets the mean, or the standard deviation gets smaller in that sense, and so there'll be less chances or less probability the farther you get away from the mean. So more interpretations. Given the safe capacity of the water taxi to be 3,500 pounds, there's a fairly good chance, and they measure the chance by the probability of 32.28%. There's a fairly good chance that it will be overloaded with 20 randomly selected men. Okay. All right. A few more slides here that won't really, or this one last slide that talks about the correction for a finite population. Sometimes they throw this in as a correction factor, but we don't have to worry about that. So that is the end of this chapter, and this is part of this stuff will be covered in the exam as well. So it would be a good thing to study and good thing to be able to do these problems. Your homework problems will focus on these sampling sizes, and they usually come in conjunction with a a comparison between a sampling distribution and a regular distribution. All right, that's it.